Thank you for having me. I have to say, Antwerp is an impressive city. Right. So let's start. I understand that not everyone is an expert in modular forms in the audience. So let's start with defining the upper half plane. So we're back in our complex analysis course. And so these are the points space of all complex numbers with positive imaginary part. And we do know that SL2R acts on H by Möbius transformation. So G tau A tau plus B divided by C tau plus D. And if you look at the stabilizer of the base point, the square root of -1, it's SO2, and that gives you, in fact, a symmetric space. So that gives you a topological isomorphism of this kind. And so you act on this way. So, and if you take, say, SL2Z, acting on H by our Möbius transformation, then you get a famous standard. So you don't act transitively, so you get a fundamental domain for the equivalence classes. And so in any case, you act and you get the modular curve, which for the purposes of this talk, I might call x prime. And SL2Z is gamma prime. So you look at all the equivalence classes, and a fundamental domain for the action is this picture. It's -1/2, here it's 1/2. And this is the square root of -1. So, and in fact, as a Riemann surface, this is the Riemann sphere. So if you want to, from that perspective, it's a bit boring, but in general, we don't have to consider SL2Z, but some congruent subgroup gamma prime, so which is a particular a subgroup of finite index. And then you get a Riemann surface with higher genus in general. And then a modular form. For my subgroup gamma prime and weight K is a function f on the upper half plane, which is holomorphic and transforms nicely under the Möbius transformation, such that f gamma tau, the Möbius transformation, gives you C tau plus D to the K f of tau. And that has to be true for all gamma in the group. Holomorphic. Holomorphic, yeah, sorry. So, and you might wonder, where on earth does the column of your matrix show up? Not today. Just, there are very good reasons, but let's leave it at this. And your matrix T, or this one, say is in your group. Say is in your group, and we typically assume this or some power thereof. Well, then f of tau plus 1 is f of tau, so f is periodic, and together with holomorphicity, that means f comes as a Q series. and Q is equal to e to the 2 pi I. So basically you write down f as a periodic function, as a Fourier expansion, and since you're holomorphic, it has this form there. To be a modular form, you need a bit more in the conditions, but we ignore that. A modular form is something which transforms under this Möbius transformation in a nice way, is holomorphic, and a bit more basically that here your Q expansion starts at 0 and not at -infinity. Or as to know is holomorphic and infinity. Right, so, and why do we care about modular forms? Basically, whenever you have, because they occur, well, it's a bit more than that. They also, particularly if you look at this higher weight, for weight 2, they give you, they represent the cohomology classes, the first cohomology classes of your Riemann surface. So that would be one reason, and that also persistent for higher weight. And moreover, they occur in arithmetic. Whenever you have a generating series, your first reflex should be, is it a modular form? And if it is, then you're in great shape, because the vector space of modular forms for the given group gamma prime and weight k is finite dimensional, and it comes with so much more structure. So if you have your generating series, and which is modular, and say you have a basis for which you do know the Fourier coefficients, then you can express your generating series in terms of the known basis, and you get formulas for the Fourier coefficients. Or you apply the additional structure, say Hecke, so-called Hecke structure on your space of modular forms, and you get some other properties of those. Or you get growth of these coefficients, and so on. So that might be some reason why we care about modular forms. So one way of constructing modular forms is via theta series. So you start with a quadratic space over the rational numbers. So there's your quadratic form over a field. So far life is good. And let's assume it's partially definite for the moment, and the dimension is m. And everything I will say, well, there will always be something which isn't quite true. But here's the first thing is, if m is odd, everything I will say today is as odd as it isn't quite true, but we ignore that. So that's the first thing is m is even, except very, very quickly I will restrict to m is equal to 3. But that's fine. It's not important. So I have my quadratic space, I have my bilinear form, which is 1/2 of the quadratic form, of the bilinear form. So it's right. And we let L be an even lattice in V, and this implies, I won't now go into what even here now means in that context, but in particular it means that the quadratic form takes integral values, meaning the bilinear form takes even values. Right. Okay, and then you can form the theta series associated to this lattice L and the quadratic form, which is you sum over all the lattice points and form the generating series q, well, q to the qx, well, that's bad, e to the 2 pi I q of x tau, where tau is my element in the upper half. And since my form is positive definite and is even, taking integral values, I can sort this from 0 to infinity by the length of the vectors r L of n q to the n, where r L of n is the number of ways or the number of times q takes the value n. So the number of vectors in your lattice of length n. So say your quadratic forms the sums of squares, then you're looking at the integral points on your sphere. And you form your generating series, and what did I say? Whenever you have a generating series, you want it to be modular, and it is true. This is a modular form of weight m over 2 for some congruent sample, which I won't specify in this context. In general, I simply won't. It is something there, it's not too important. Think about it for SL2Z and you're in great shape. So for the, and in this way, there is what people call the analytic theory of quadratic forms. You take your positive definite quadratic form, you form the theta series, you're in the space of modular forms, and say, morally speaking, for example, you might have more quadratic form than the space of modular forms, so then its dimension. That means you might get linear relations between these representation numbers, even if these lattices are not equivalent. So, and so on. So there's quite a bit of potential arithmetic in there. You wonder, what is the proof for this? Why on earth does this give rise to modular forms? It has two aspects for this. For the sort of the proof idea, it is really harmonic analysis, constant summation, and this comes to the fact. So constant summation is when you have a function on the real line, say, or in Euclidean space, you take its Fourier transform, you sum over the lattice, and the function, then this is the same, is equal to the summation over the dual lattice of the Fourier transform. And if one applies this cleverly, then this gives rise to a modular form. The exact is an eigenfunction. So this is an eigenfunction on the transform. We'll use, and the exact determination of gamma prime, of what group it actually is, that's a bit fiddly, which I won't say anything today either. So that's fiddly. Does one spell fiddly with 2D or with 1D? 2D. 2D looks better, doesn't it? So we maybe don't want to go into this. So And in fact, say for the sums of for a low number of squares, 2, 4, 6, and 8 squares, this gives you exact formulas in terms of divisor sums for the sums of squares. There's another example. If you look at the E8 root system and look at the ladders associated to this, this is a unimodular lattice, so it's equal to its dual lattice. Then this gives rise to a modular form for SL2Z of weight 4. The space is one-dimensional, generated by a so-called Eisenstein series, which I mentioned later. And hence you get an identity between divisor sums and the number of vectors of a given length in the E8 root system lattice. And many other similar games one can play. You can slightly generalize this to, if you take P of X to be a harmonic, a homogeneous polynomial degree L of degree L, and it's harmonic. Then you can form the theta series for tau for the lattice L and for my polynomial P in a very similar fashion. I sum over the lattice. I now weight the lattice vectors by the values on the polynomial, but then otherwise do the same thing. So if P is the trivial polynomial 1, this is the theta series from before, and this gives you a modular form of weight m plus L, where L was the degree of the polynomial. And roughly speaking, the proof is the same thing. When you write P of X times the Gaussian, you look at the Fourier transform thereof, you get it's an eigenfunction thereof, and then the proof goes along the same lines. Okay, so, and please allow me not to say anything more about this, about the representation theoretic context and so on. This is just the black box. Theta series, by means of harmonic analysis, give rise to modular forms. And that's great news.
Can I ask you something? Is the group sensitive to the P or
not? No, P. No, this is say in terms of arithmetic, P is something which happens at the infinite prime, and whatever happens at the finite primes, which is really determining the gamma prime, that's all in the lattice. And by the way, there is the next thing which I've been lying about. If P has odd degree, then this would vanish identically. Well, you have to then deform the lattice to a coset and so on to break the symmetry. Never mind, it's fine. Right. So this is the positive definite, which raises the question, can I do this for indefinite lattices? So I have a positive definite. So that's perfect. Right. But you're immediately in deep trouble here. If you write, so L is now indefinite, or V is indefinite. Well, then if you just write down this, your convergence will no longer work. So you have serious convergence issues. But also, if you say, okay, this doesn't work. Well, that doesn't work either, because these representation numbers for indefinite quadratic forms are typically infinite. So these R L of n is typically infinite. So we are in trouble. But there are examples where this works for indefinite spaces. And let me give you 3 examples thereof. The first one is the so-called Eisenstein series. And that's maybe should have been the example I've given right after the definition of modular forms. Now it comes. Well, it's the constant term A0 is the Bernoulli number, bk divided by 2k. So that's Bernoulli number, some rational number, plus the generating series of the divisor sums. So this is the sum over all the divisors of n to the power k minus 1. Oh, sorry. So Eisenstein series is the sum from 1 to infinity, the coefficient sigma k minus 1 of n, the sum of all the divisors, positive divisors of n, to the k minus first power. And this is a modular form of weight k, in fact, for SL2. The Eisenstein series is not defined in this way, but it's defined in a way where the modularity is obvious. You basically take a function and then average it out to be modular for SL2Z per definition, and then you compute the Fourier expansion and this pops out, and then this is the miracle. So whereas here, with the theta series, writing it down was obvious, and then the miracle was it's modular. With the definition of the Eisenstein series, the modularity is clear, the miracle is the Fourier expansion, particularly that the coefficients are all rational, even though the construction is very transcendental. Somebody want to ask?
Yeah. Can you, so can one write down the theta series as this?
Yeah, well, yeah, that's gonna come.
Okay, as average.
Hang on. Yeah, well, you can think about it. Well, maybe, of course, the word theta series, maybe this is not, maybe, well, depending on what you mean by theta series. But let me write this down. So, and I claim that this is an indefinite theta series. Oh, by the way, k needs to be at least 4 in to be this. Oh yeah, so that's a modular form. And I rewrite the divisor sum in the following way, that this is the sum over all integers, positive pairs of integers x, y, x to the k minus 1, q, my q series variable, x times y. X, y. So why is this the case? You write n, there was the divisor, as x times y, or d times d prime, as the divisors. Then d sits inside m, gets the power k minus 1. So if you just stare at this and this is the same thing. Right. This is an indefinite theta series. Now, V in that case would be two-dimensional. The lattice would be z squared, and my quadratic form is x times y. And my harmonic polynomial would be x to the k minus 1 if you define the right version of the Laplace operator, namely the one associated to the indefinite quadratic form. So this is very much of this form. My two problems I had get fixed by I restrict the summation over the positive cone. So no vectors of negative length show up. So here the exponent is always positive. I don't have to worry about convergence in this regard. And okay, there is a bit of cheating. For that particular quadratic form, the representation numbers are finite because a given integer n has only finitely many devices. But never mind. So,
But over the positive ones.
sorry?
Over the positive ones.
Yes, over the
Fine.
well, also over the negative ones, the representation numbers will be also finite because every integer is only finitely many devices.
Yes.
Yes, so it's right. But and by the way, you could prove this using a Poisson summation argument. You write down some function x to the k minus 1 times the Gaussian associated to this there times the indicator function for the positive cones, and then run the Poisson summation argument through this. It works. I'm not advising doing it because how on earth in that context do you get the Bernoulli number showing up? That's one question. The other thing is, if you try to do it that way, you will need to use that k is at least 4. For k equals to 2, this object exists, but it's not quite modular. It wants to be modular, but not quite. And that is actually interesting. The proof idea for a higher k would also work. For k equals to 2, you just go through, pick k and so on. Eigenfunction on this, blah, blah, blah. But then Poisson summation doesn't hold. Poisson summation holds for nice functions, say Schwartz functions, and so on. But if you do this for k equals to 2, Poisson summation doesn't work. It breaks down. So, you know, the people who are doing harmonic analysis, they're of course really worrying about for which function Poisson summation doesn't go. It does not follow. Okay, let's do it. Right. So that's one example. And what is my time? I saw I have till 20 past or so. Okay. So maybe I skip example number 2 and go to number 3, straight to number 3. Actually, that's the 2, which goes back to Hecker from the 1960s. In that case, V would be a real quadratic field. Your lattice L would be the ring of integers of K, of the field. The quadratic form of an element lambda, and there would be the norm of lambda. So lambda times lambda bar. So it has signature 1, 1, so one positive and one negative eigenvalue. So it's the non-split version of this quadratic form. And I let gamma be the units. Okay, maybe the positive units. And then Hecke writes down the following thing. He sums. So my element lambda can be typically written as x plus the square root of dy. And now I sum over all the elements in my lattice. Okay. I assume that the norm of lambda is positive. Again, the positive cone condition. But now I really have to be careful with my representation numbers. But modulo the units, I only have finitely many vectors of a given norm n. I take the sign of x, this bit there of lambda, and then the same thing as before, q to the norm of lambda. And this is, well, modular form, in fact, the cusp form of weight 1. So again, the same principle. It's signature 1, 1. Now I solve my problems by summing over positive cone. My representation numbers, well, I do have a unit group, so I mod out by this, and I form that. And this is a very funny harmonic polynomial in that context of degree sigma. This is wrongly stated because of the sign condition. Again, x and minus x would give you opposite contributions, so it went identically. Again, you have to do a slight deformation of this, but the idea is again there. By the way, you can play this game certainly for imaginary quadratic fields. But then you're in the positive definite case, and you get modular forms of weight 1, which are highly interesting. In term 1.
What's the compose of gamma prime here?
What's the gamma prime? What's gamma prime? The level is, well, roughly d.
Yeah.
Close enough. Okay.
Yeah.
And the third example is the one given by Spekas. And it's very different and very different in nature. So the signature, so the number of positive and negative eigenvalues is p, 1. So, okay, so, and I take two vectors, and they don't have to be rational, of negative length. They don't have to be of length -1, but that makes my life simpler. What surprisingly, you will see later on plays a role is that the inner product is negative. Okay. And we make a detour through statistics. E of t is the error function. Well, slightly differently normalized, the error function. And then what Sanders in his celebrated thesis showed so he writes down the following thing. It's a theta series, Z for, sorry, my mind writing is a disaster.
What's the name?
Sanders Vegas. Sanders.
Yes.
Yes. Native language Dutch. I'm afraid he's not Flemish though. So he defines a theta series associated to this theta. So hyperbolic space here, two vectors of negative length, and the error function. Namely, the sum over all the lattice points. Right, and let me just put here plus h. That's my deformation to make the whole thing non-vanishing. 1/2 for cosmetics, and then the error function of evaluated at the inner product of my vector x with c1. The square root of 3 can be safely ignored. The square root of 2 can be safely ignored. Yes. Q to the qx. So what on earth is this? So you have your two vectors, C1 and C2 in your space. You sum over your lattice, take the inner products, and I evaluate them at the error functions and look at the difference. And the claim is that this is now, oh, sorry, I forgot the decisive points. Here is the square root of v in there, and here's the square root of v. And remember, v was the imaginary part of time. This is a non-holomorphic modular form because v is there. Of weight p plus 1 over 2 for some congruent subgroup gamma. And I'm going to come to a minute to why on earth we might care. So the proof is the same as what we did before, or what people did before, constant summation. So one writes down the appropriate object, this minus this times the Gaussian, and shows that this is an eigenfunction under the Fourier transform. Then one really has to worry about quite a bit actually, that the constant summation can be applied, and then one gets the modularity from this. But why on earth would we care? The error function if you complete it, of course, then you get the value of 1 or 2, depending on you do this. And of course, this might be positive or negative. So if you let this go to infinity, you have something up there, positive, negative, so well, then you went to minus infinity. So if I complete this, going from the error function to the complete interval, I get here the sum over my lattice, the sine of x, and the inner product with C1 times the sine of x with C2, q to the qx. But of course, that isn't the same. And the difference of this and that is, well, the complementary error function, maybe the integral from t to infinity. So plus the non-holomorphic rest. Which is this minus this. I'm not going to write it down, but it's clearly non-holomorphic. But it has something to do with the error function. And now comes the thing. As it turns out, if x has negative length, these two terms always cancel. And I will give an explanation for this at the end of the talk. So this, if x has negative length and if x has zero length as well. So automatically, my positive cone condition kicks in. Just by the fact that if x is negative length, these two terms will always cancel. I will give an explanation for this later. And now the entire way of thinking about this changes in the following way. Say you start with this object. There is your Q series, which you want to be modular. It only goes over vectors of positive length, so converging everything is the case, so it's not a problem. So you write on this object. Unfortunately, it is not modular, but you can complete it to something modular at the price of making it non-holomorphic. And it's very explicit, in particular, since the error function and so satisfies certain differential equations, so does this. So roughly speaking, which is not quite the case, you get something which is no longer holomorphic but harmonic. Why did Swagers care about this? Similar function to these were defined by Ramanujan in his very last year of existence, which he called mock theta functions, and which he attributed various exciting properties, couldn't prove, which then some of them were then proven following Swagers, who turned this into an object of modular forms, even though non-standard modular forms. And then one could say something about these mock theta functions. So that was one of the exciting applications of this stuff. Okay.
So when you say mock, it means like it's something that then if I add a non-holomorphic.
Yeah, exactly. So the mock modular form is a generating series which wants to be modular, but it's not. But it can be made modular by adding something non-holomorphic to it. And this non-holomorphic is not just some random stuff, but has certain analytic properties, say being harmonic. Yeah.
Is finitely dimensional?
Pardon?
Is this space finitely dimensional?
Pardon?
The space of where this set of
Oh yeah. No, I mean this again would vanish.
Okay.
So I again need my deformation.
No, we ask if it's finite dimensional.
Oh no, these things are not.
Okay.
But they are not that badly infinite. Ask me after the talk, okay?
So when you say not that bad, you mean that there is like a basis or something?
Well, no. Yeah, well. How much time do you have? I have 1.5 hours left. Is that what you said? Yes, okay, sorry. So, what about the geometry background of this? So V has signature in general, P, Q. Let G be the special orthogonal group of real points. In there, I have the maximum compact subgroup, which is exactly the picture I had for SL2 and SO2. So I look at the associated symmetric space, G mod K, the symmetric space, which I can realize in a projective way that these are the negative Q planes. So my bilinear form will be restricted to this of maximum dimension, and I do want them to come with an orientation. And the way how you can see this is G acts on this space linearly, and maximum compact subgroup SOP times SOQ is in fact a stabilizer of one of its ones. So these are the generalizations of the upper half plane. And in fact, if the signature is 1, 2, then D is the upper half plane. Well, and for signature 2, 1, it's also the upper half plane. Now, for P, 2, in general, D is Hermitian. And for P, 1, we're looking at hyperbolic space. Hyperbolic P space. So I have 15 minutes, be right back. So I take gamma something in the stabilizer of my lattice. And then X becomes B mod gamma. That's my symmetric, locally symmetric space, my Riemannian manifold, which, if Q is equal to 2, always gives you a quasi-projective algebraic variety over the complex numbers. So these are nice algebraic objects. But these are very natural spaces you could construct in this way. And you wonder about what is this cohomology or other objects there. And Paul is getting a bit of a crisis that I'm running out of time. No, you're not? Or all under control. Fine. So we have these spaces, we have the projective realization. So now we have, let's take a back. So one of the questions is, what is the cohomology? That's a very natural thing, and then of course in comes in all kinds of flavors, but for cohomology, it's always good to having some homology classes, some cycles. So I take a vector x in L, which has positive length. And then I define dx to be all my negative Q planes which are perpendicular to x. And that's a subsymmetric space of dimension of signature P minus 1, Q. So x is a vector of positive length. You restrict to all the negative Q planes which are perpendicular to x. So you cut out one positive number and you're there. You look at gamma x to be the stabilizer of x in gamma. And then you look at the quotient dx modulo x in your symmetric space x. And that's the example. I will really need to worry about my time. So which I have to cut down is, so let's look at signature p, 2, 1. That's the one maybe I care about the most for the moment. Signature 2, 1, D is the upper half. Then dx is a space of signature 1, 1, which is a line. The upper half plane is here. It's a geodesic. So the cycles here are the geodesics in the upper half plane given by semicircles or vertical lines. And then I mod out by gamma x, which then typically makes them compact, close geodesic in your modular curves, defining objects in H1 of x. And so these are the ones. You can form, given n, given x, you can look at all the objects in L of length n, positive, and I look at all the cycles together. These are infinitely many. We already have that at Hecke's example. I have to mod out by gamma to make them finitely many. That was the picture here. L is gamma was the stabilizer of the lattice. If you have a given length, mod the stabilizer of the lattice, you get something finite, and you can sum these objects up. And these are in general non-compact cycles, but they're just cycles. If signature is p, 2, then you would actually get algebraic cycles in that way. So the theorem of Kudla and Nielsen in much greater generality is, if you look at the generating series, so you take C, a homology class of complementary degree, the degree so that you can do the intersections with these cycles, whatever that degree now is. Then the sum, the generating series of these cycles, and then you take the intersection product. How do I do intersection product? Maybe like this. In cohomology, say from 0 to infinity. I'm not saying what 0 is. Q to the n. This becomes a modular form of weight p plus q over 2. So this gives you a gigantic supply of holomorphic modular forms associated to indefinite quadratic forms. So this is stuff which started in the 70s and ended in the 80s. So you take your cycles, you intersect them with a given complementary cycle, take the intersection numbers, write down the generating series, and you get a module. The Hecke thing comes in there when you intersect with the entire thing. The Eisenstein example can also be interpreted as in this way, but that goes back to work I've done with Nielsen later on. And the question is, can you understand Zweigers in this way? And the answer is yes. So how did Kudla and Nielsen prove this? they defined a theta function in two variables. It's modular of weight p plus q over 2, and here it's a differential q form on my orthogonal variety x. So it's q form, so that thing in fact was q. And then you can integrate this in the z variable over your q cycle. It becomes a function in tau, and then various miracles happen, and you get this. Of course, the miracles are very well motivated by the kind. So they take a universal theta function, modular in the SL2 variable, a differential q form on x, and you integrate this one over the cycle, and you get something modular. You can generalize this to cycles with coefficients, non-trivial coefficient system. So I've done this with Milson, and in that way, then you can actually get this Eisenstein series example as an indefinite product form. Which brings us to spheres. And this is now joint work with Steve Kudla. And it's really the generalization to this to arbitrary signatures, which I won't come into. Right. So we are in Schweger's situation. Hyperbolic p-space. P equals to 2, my upper half. I have two vectors of negative length. The condition means the hyperbolic space is the space of negative lines. Two vectors of negative length then define you 2 points in the symmetric space. C1 and C2. Points of negative length define you 2 points. The condition on the inner product means they are in the same connected component of the symmetric space. Because the symmetric space were the ones with 2 different orientations. So this condition is the same connected. So what we did is, so you have this. We in signature p, 1, everything is so as before. You connect them with a curve gamma, any curve, gamma. And then the theorem is when you integrate the Kudla-Milson form over that curve gamma. That's a 1 form. This is a curve you can happily integrate over 1 form. You get something modular. You get Schweger's function. Points. The curve doesn't matter. This is a closed differential form. If you take a different curve, you're integrating over something simply connected, you get the same thing. But moreover, because of the intersection property of this intersectional properties, what's happening is the following. The cycles are my geodesics. This intersection number, the sign, the difference of this bit becomes the intersection number locally of dx with my curve gamma. Meaning if gamma intersects the curve, you get plus or minus 1 depending on the orientations, and here you get 0. The sign would not change. And for vectors of negative length, there are no cycles. The sign will not, the geometry will tell you it will never change. Moreover, if these 2 points were gamma equivalent, then this curve will give you a closed curve, defining you an element in here, and you get something holomorphic, because in that case, the rest, this bit and that bit will cancel each other, and the non-holomorphic part goes away. In case you wonder when does the non-holomorphic part goes away, exactly when the 2 points are equivalent under the stabilizer of the lattice, you get integrating over closed curve and Kudla-Mills. Swegers was generalized by mathematical physicists in the context of string theory, and then first to signature p,2 and then arbitrary signature. The method is the one so far from them. Again, they're using the before you apply Poisson summation and you have to really worry about Poisson summation. In our case, we don't have to worry about this thing. We know that this is modular, this is compact. We can compute that integral termwise. So all the analytic problems go away. And because of the geometric properties, you also get a geometric interpretation of the holomorphic. And now you can play this for many other signatures. But the general idea is then you get modular forms whose coefficients give you, well, really linking numbers. This is really the linking number of the cycle with the 2 points, plus the modular completions. Many more games to play. My time is more than up. Thank you very much.
Yes, thank you for the talk. Are there any questions?
Can I ask another question? So this modularity is a phenomenon that appears when you look at the closure, this X. Right? When you look at the same generated series of Kudla-Mills, but over this compactification. Can one read?
No, it's not about the compactification. Well, that's a different game.
Yes.
That's a different game.
I agree. Then you enlarge the pool of curves that you can.
Yes, indeed. So that is something actually comes in. So here, of course, these cycles are relative cycles. That means you can only pair them with compact cycles. Of course, now you would like to extend this to the appropriate compactification. Now you need to tell me, do you care about the algebraic case signature p,2, where we have almost yes, I was afraid of that. Yes. Or do you care about the general situation? It depends then on the compactifications. The answer is yes, but there are various versions of these kinds of theorems. Bonnier and his collaborators have been working on this. I've done some work with Milson about this. It depends partly on the compactification you employ. Say whether use what kind of it will depend on the kind of toroidal compactification you use. But there are also this kind of theorems or some kind of theorems in the real case. And then you no longer have, then you have different compactifications, so-called Borel-Serre compactifications, which makes the entire thing into a manifold with boundary. But that's a different game. Or you try to prove these kind of results in L2 cohomology wires. I don't know, weighted or intersection homology statements like this. This is probably the proper setting for this.
Can you do this also with coefficients? Like in the Funke style?
One should. One should. And okay, so for say for signature 1,1, or no, even the case I just had written down here. What happens if you move these points to the boundary? You're integrating over something non-compact. You can do this, and it actually converges, but not term-wise. You have to be careful. You have to assume that these are no rational cusps, and then you get something holomorphic. And if you do this then with coefficients, you get this isostat series. So, which of course then pushing these two points onto the boundaries, of course, related to your question about the non-compact situation.
But do these physicists have like some version of this with coefficients? Or?
Yeah, they mumbled something along there as well. We can apply some differential operators. Yes, I mean, the intuition of the mathematical physicists involved is spectacular in this. And that was really our motivation for becoming from this. And, however, not all of their intuitions or statements have been actually correct. For some of them, we actually, our proof was producing something different. And then it really puzzled us about the statement of the physicists, but eventually they conceded, said, yeah, we were wrong, you should write so. And we were too polite to formulate it in that way. No, there is quite a bit of gold still to be found. Also in terms of Appel functions, Jacobi forms, but that's it. So sorry.
Then let's begin again.